Hello, everybody. Today, let's look at sustainable solutions for energy management. The topic for today's presentation is integrating microgrid controllers with local utilities, evolutions in IEEE standards, and the BESS integration challenges. BESS stands for Battery Energy Storage System. My name is Xinsheng. I serve at ISA, and currently I'm the direct leg for ISA's power industry division. This conference was organized by IEEE. Mr. Mike Brisbois, my friend, invited me to give a talk on this subject. Mike is actually an expert on a microgrid, so he guided me to prepare this presentation, microgrid controllers, and talk about the IEEE standards on distributed energy resources integration. So this is a virtual conference hosted by Mike and his committee members on March 22nd, 2024. Here's the agenda for today. First, let's look at the definition of microgrid and the critical roles of microgrid controller. Then let's look at IEEE 1547 and IEEE 2030, as well as other relative standards from other organizations. Then we'll look at the NERC standards for compliance. After that, let's look at the battery energy storage systems, integration of BESS, and the challenges. Then we'll look at the microgrid controls, in particular resilience with dynamic boundaries. After that, we can have question and answers. And here, if you have a question, just add to the comment area. So, what is a microgrid? So, microgrid is a localized group of electricity resources and the loads that can operate independently from traditional centralized large electrical grids or in parallel with that. So here is a picture generated by ChatGPT. So we have a battery, we have a solar panel on the roof, and solar panel on the ground, and we have a wind farms, and the houses, the loads, which we have other loads that consumes the power. So microgrids is a concept that's against conventional logic grid. So microgrid controllers are sophisticated systems designed to manage and control microgrids. Microgrid controllers assume very crucial roles in operating power systems. First, it helps manage energy resources. It helps ensure reliability and stability of the power systems. It helps optimize the performance of the power system. It helps automate the operation of the power system, including the large power grids and microgrid. So, what are the two IEEE standards, 1547 and 2030? Both 1547 and 2030 are critical standards for integration of distributed resources with the large electrical power system, focused on integration and interoperability of distributed energy resources, DERs, with the electrical power grid. 1547 provides the standards of interconnection and interoperability of DERs with the power system. 2030 provides a guide for smart grid interoperability of energy technology, information technology, operation with electrical power system, and the user application and the load. This picture shows how IEEE 1547 evolved in the past 2 decades. In 2003, IEEE 1547 was first established to standardize the interconnection and interoperability for distribution energy resources integration with large electrical power grid systems. In 2013, 2014, IEEE 1547 received a major amendment. And 2018, there's another major revision. 2021, another important item was added on compliant component for commercial applications. So, what is the scope of IEEE 1547? So, what is the coverage? So, there's technical specifications, which includes voltage, frequency, power quality, and islanding mode. We also look at the testing and certification. Also, we look at the engineering system design, involve the guidelines for physical and logical integration of distributed energy resources. All these apply to PVs, wind turbines, battery energy storage systems, and other distributed energy resources. So, what are the major challenges facing microgrid integration and IEEE 1547? So, the current challenges including cybersecurity, regulatory compliance at the state level and the federal level, and several technical integration challenges. The technical integration challenges including managing the complexity of integrating the DERs. We're adding more and more DERs. And how can we handle all this and manage all these integration cases without compromising grid reliability? The future directions for 1547 including ongoing updates to address emerging technologies and grid modernization needs at the state level and federal level. And we should look at how to enhance resilience against natural disasters, earthquakes, tornadoes, hurricanes, and also we need to deal with cybersecurity. And we need to foster collaborations among stakeholders to achieve smooth integration of distributed energy resources. Now let's look at IEEE 2030. As we said before, 2030 was initially developed to provide guidelines on interoperability of a smart grid, energy technology, information technology in operation with the electrical power systems, end user applications, and electrical loads. The timeline is like this. The first version of IEEE 2030 was introduced in the year of 2011. And subsequently, there are serious updates, which include reflecting the rapid advancement in smart grid technologies, communication protocols, and integration frameworks. The key milestones including how to address the integration of renewables, distributed resources, electrical vehicles, smart buildings, battery energy storage, so on and so forth. This slide talks about IEEE 2030's scope. On the right-hand side, we have a picture that describes the smart grid operations. The first level is smart grid concept reference models, and the second level includes the IEEE 2030 standards for smart grid interoperability, and the lower level, the bottom level, is about smart grid operations. So again, this is also about utilities, energy services providers, and technology developers. End users and consumers can benefit from the enhanced grid capabilities through the application of 2030. The challenges include technology integration, regulatory and policy alignment, and resilience and the reliability of the power grid systems. The future work should include continuous evolution of the standard to address the dynamic nature of smart grid technologies, and the global energy landscape. This slide lists the three major aspects of the latest updates in IEEE 2030. The first one is cybersecurity enhancement. The second one is advanced communication technologies used in smart grid. And the third one is the sustainability of a smart grid with more and more renewable and energy storage system and electrical loads are being added to the grid systems. This slide gives more practical tips for microgrid control design. So you can read all the text in detail. Here, just walk through this very quickly. First, harmonizing technical and operational requirements. Second, designing for flexibility and scalability. Third, ensure cybersecurity and resilience is being considered. Compliance and testing should be considered and enforced. We have reviewed IEEE 1547 and IEEE 2030, and these slides introduce NERC standards for microgrid integration. NERC stands for North American Electrical Reliability Corporation. NERC produces a series of industrial standards for electrical system operation compliance. And NERC has some standard items that provide guidelines for reliability and security for smart grid integration and microgrid integration, how to integrate distributed energy resources within the broad grid framework, and make sure it's safe, reliable, and resilient. And the compliance with NERC standards complements the technical and operational guidelines from IEEE standards, such as 1547, 2030, and other relevant standards. This slide is more tips for using NERC standards together with IEEE 2030 and IEEE 1547 for microgrid integration. These key points are listed here. First, the critical infrastructure protection standards, CIP, such as CIP 002, CIP 014. And the second item is about protection and the relay. One example is PRC 005. And besides, there are standard items that provide guidelines on modeling, data collection and processing, and data analysis. These slides help us move into the subject of BESS, battery energy storage system, which is an important part of renewable energy system. And on the right-hand side, we saw the typical bell curve. And in today's power system, the bell curve is even involved into a Grand Canyon curve. So the ups and downs of the grid is sharper than before. So the bottom picture on the right-hand side shows the microgrid compositions. So power system flexibility is a key thing. So BES is a solution for consistent energy supply when more solar and wind power have been introduced to the power system as intermittent resources. This slide basically shows how battery energy storage system helps the operation of power grid with renewable energy. In the green part, you saw the battery discharge power when the grid demand is higher than the capacity of generation resources. On the other hand, the pink part shows the situations where the demand is low and the power generation capacity is higher than the low demand. In this case, the extra power or surplus power can be saved or stored to the battery. So, and this also involves the economic optimization because at peak power and the low load, uh, the the power system operators will give different prices for supporting the grid operation, support the flexible operation of the grid. So this involves the economic optimization by taking advantage of the energy storage resources, distributed power, such as PVs, electrical vehicles, small wind powers, or diesel engines, things like this. Talk about the BESS operation and integration into microgrids. Safety is the first thing to consider. These are the standards other than IEEE standards, but they are very important in engineering design and operating considerations. First, let's look at the UL standards, UL 9540 and UL 9540A. And other standards also include IEC standard, IEC 62485. This is a standard for safety requirements for secondary batteries and battery installation. Another IEC standard is 62933, electrical energy storage systems. And these work together with IEEE standards to ensure safety, performance, and interoperability of the microgrid with BESS. This slide talks more about the sub-items under IEEE 2030. Here, we list IEEE 2030.2, .7, and .8. And beyond that, there's a standard IEEE P2800. Although it is not exclusively designed for microgrid, IEEE P2800 is a standard for interconnection of microgrid and interoperability of inverter-based resources in particular, because inverter resources is very important for integrating like PV, solar PV, and battery energy storage system. Inverter basically convert DC resources into AC resources. This slide talks about the resilience in microgrid operations. By definition, resilience in microgrid operations refers to the ability of the microgrid to prepare for, withstand, recover from, and adapt to adverse conditions, disturbances, or attacks. This includes natural disasters such as hurricane, earthquake, and floods, human-made events such as cyber attacks, and physical sabotage, the technical failures within the grid infrastructure, so on and so forth. This slide introduces a new concept of dynamic boundaries, which is against static boundaries. The concept of a dynamic boundary in microgrid operation refers to the ability to adjust the microgrid's operational boundaries in real time based on the various factors, such as load demand, availability of distributed generation resources, grid conditions, and economic considerations. And the key features include scalability, flexibility, islanded and grid-connected operating modes, and optimization of the operation of microgrid with dynamic boundaries. This slide continues from the last one, which introduced dynamic boundaries. On this slide, we list more technical items for dynamic boundaries of microgrid operations, real-time data analytics platform, automatic control systems, distributed energy sources controllers, energy storage systems, communication networks, smart sensors, and IoT devices for detailed monitoring of grid conditions and resource utilization, and the software tools for optimization of the grid operations. This slide continues from the last slide, which listed the technical items for dynamic boundaries design and operation. And this slide focuses on the use of MILP, mixed integer linear programming, one of the several options for optimization of microgrid configurations. And at the bottom of the slide, we list the reference. The paper give example of dynamic boundary operations using MILP in particular. This slide continues from the last few slides, talking about the dynamic boundaries in microgrid operations. One key item on this slide is highlighted here as IEEE 123 bus system. IEEE 123 bus system refers to typical American towns distribution system operation guidelines. And on the right-hand side, there's a diagram, like the example of an online diagram for modified IEEE 123 node test. And from the paper, it proves that there's a significant improvement in network resilience and critical load support with dynamic boundaries. This slide showed example of microgrid configuration using dynamic boundary techniques. On the left-hand side, there are 4 microgrids, mu1, mu2, mu3 for the upper region, and mu4 for the lower part. And in total, there are 4 microgrids for daytime operation. On the right-hand side, mu1, mu2, mu3 are combined into a single microgrid, mu1, and the bottom area is considered to be a single microgrid still. So at nighttime, there are only 2 microgrid operations. And the study shows with dynamic boundary, it demonstrates the self-healing capability in microgrid operations. This slide provides an overall summary. First, microgrid controls will play an increasingly critical role in overall power system operations. IEEE 1547 specifies the requirement and the recommendations for connecting distributed energy resources to the conventional power systems. IEEE 2030 focuses on integration of smart grid. Beyond IEEE standards, we also look at NERC, UL, and IEC standards that supports the integration of microgrids and battery energy storage system. We also look at the dynamic boundary, which is a technique for enhancing the resilience of microgrid integration and operations. Thank you for paying attention to my presentation. If you have any question, please add to the comment area or send an email to me. And also here, there's a URL for my LinkedIn profile. Please feel free to send me a LinkedIn invitation so we get connected as professional colleagues on LinkedIn platform. And also, I serve at ISA, International Society of Automation, and its a division of power industries. So if you have any question about ISA or power industry division, please feel free to send me an email as well. Thank you.